In this video, we're going to look at how we can solve some differential equations using what's known as the net change theorem. Now, the good news is that we already know the net change theorem, so we're going to talk about how that basically comes from our fundamental theorem of calculus. And we know that the fundamental theorem of calculus part 2 tells us that if we want to find the integral from a to b for some function, here I have it called f prime of x dx, is that if I evaluate this and I find the antiderivative of this guy, which I would call just capital F of x, then the antiderivative evaluated at the upper value, or the upper limit, minus the antiderivative evaluated at the lower limit would give me f of b minus f of a, where f of x is equal to the antiderivative of f prime of x there. So in many applications, when we're thinking about this, because we're subtracting a function at its endpoint minus the function at its starting point, we view that as net change over time. And a classic example of net change would be distance traveled. And so basically the net change theorem just expands our idea of the FTC part 2 to tell us that the integral of a rate of change is the net rate of change. That makes sense, right? So what it's really saying is that if you have, let's say, position, and you're starting here at position 2, and then you move to the right and end at position 8, well, your net change would be the 6 units in between 2 and 8. So as we're going through, what we're going to start doing is connecting the integral to this idea of net change. So in example 1, we're going to just kind of look at it in terms of an application, and then we're going to actually go and solve some problems involving this idea. So here I have f of x is representing the slope of a trail at some distance x miles from the start of the trail. And if I want to know what does the integral from 3 to 5 of f of x dx represent, what I need to remember is that f of x of slope is a rate of change. And we think of it as the change in y over the change in x. But if we're on a mountain, it's basically the change in elevation over time, right? As we climb up that mountain, right? So if the slope of the trail from 3 to 5, I'm looking at the change in elevation from 3 to 5. And so I'm looking at the net change. So that integral of from 3 to 5 of f of x dx, f of x is again representing the rate of change of elevation over time, because that's my slope. Then this would represent the net change in elevation from x equals 3 to x equals 5. And that's miles from our starting point. So basically, if I knew at 3 it had an elevation of 4,000 feet, and then at 5 it had an elevation of 10,000 feet, then I could find the net change by just subtracting those two values. That's all that it's really representing in this case. And the dx is representing our change in time, in this case right here. So distance equals rate times time. So the most common application of this is when we're talking about that change or that net change in position. That we call the displacement of an object. So the displacement tells me how far an object has moved from its original starting point. So on a given interval from a to b, the displacement would be found by taking the position at the end point, which would be s of b if we're using s to represent our position function, minus its original starting position at point A, and we're going to use s of a to represent that. So if we use that idea, what I'm taking is s of b minus s of a. Well, that looks a lot like my FTC up here, where I do f of b minus f of a. And if we dig a little bit deeper and we think about how position s of t is actually the antiderivative of the velocity function, we can see how the net change theorem can be applied for displacement. So this right here would now be our formula for displacement of an object. If I take its velocity, its rate of change in position over time, and multiply it by its change in time, and I sum up all the values from A to B, that would get me the displacement there, or S of B minus S of A, the antiderivative of velocity is position, and then I substitute my upper bound minus my lower bound. So let's look at an application of this and actually see some calculus put into action here. So in example 2, we're given the velocity function in meters per second for a particle moving along a line. And we want to find the displacement of the particle on the interval that's given there from 1 to 6. That's this guy right here. There's my interval. So this is my velocity function. This is my interval. I want to find the displacement. So using our net change theorem, our displacement is really just the integral from my starting point to my ending point. So from time 1 to time 6 for my velocity function, which was that t squared minus 2t minus 8 multiplied by the change in time, which would be dt. All I need to do to solve this is just use my FTC. And then the answer to that would be the displacement of this object. So I'm going to anti-differentiate this function using my basic anti-differentiation techniques. So I'm going to get 1/3 t cubed minus t squared minus 8t. I want to evaluate that indefinite integral on the interval from, or the definite integral on the value from 1 to 6, the antiderivative there. And again, what I'm going to do now is just let my calculator do the number crunching for me. So I need to go into this function, replace all of those t's with 6. So I would do 1/3 times 6 cubed minus 6 squared minus 8 times 6. Let the calculator do all that math for me, and it's going to give me that value would be -12. So that's my S of B, or S of 6 value. And now I'm going to subtract out the lower bound evaluated into that antiderivative. So I'm going to replace all of these t's with 1. Again, I used my calculator. 1/3 times 1 cubed minus 1 squared minus 8. My calculator gave me a value of -26/3. And so I went ahead and just took -12 minus -26/3. And when I did the math, I found out it was -10/3 meters. So that means that my displacement, the particle ended up moving -10/3 meters away from its starting point. So it moved 10/3 meters to the left if it's moving on a left-right line. Or if it's moving up-down, it moved 10/3 meters down from where it started from. So that's my displacement. It looks at basically the change from the starting point to the end point and tells you how far it moved on that. Now, the key thing to keep in mind is that our particle doesn't necessarily always have to move in one direction. So we know that when velocity is positive, an object moves in a positive direction. And when velocity is negative, my particle moves in a negative direction. So it's possible that this guy started, moved one way, and then turned around and moved the other way. And so its displacement would have just been that chunk from start to finish, which kind of matches up more like this guy right here. So when we're looking at this idea of net change, it doesn't matter which direction your object's moving in. It's just going to look at the final position and the starting position and find the difference between those 2 points. If I wanted to know, well, how far did this object move altogether? I want to know, well, from start to finish, what did I actually move? If I'm a runner running, I didn't actually run 10/3 meters to the left. I ran all of the space to the right and then turned around and ran all that space back. I ran more distance than it looks like based off my displacement. So when we're trying to do this, we have to distinguish between displacement and total distance traveled. So we have to really think about, what does the question want? So if the question wants displacement, I'm going to do the net change theorem and just apply FTC to my function on the interval. But if I want total distance that an object traveled, so like this particle started at 3, moved left 2 spaces, turned around, and then moved right 8 spaces. Yeah, it started at 3 and ended at 9, so its displacement was 6. But my particle really moved a total of 10 spaces. It moved 2 to the left and 8 right, so altogether it moved 10 total spaces. There's a big difference between 10 and 6. So if a question wants to know how far did an object move and what's its total distance traveled, we have to find the absolute value for any negative distances, and then we can add all of our distances together. So a lot of times you might see that represented as the integral from starting point to end point of the absolute value of your velocity function. And by throwing the absolute value bars, now we're no longer allowing velocity to be negative. But we don't know how to anti-differentiate velocity. So we have to come up with a workaround. I mean, we don't know how to anti-differentiate an absolute value. We have to come up with a workaround. So what we're actually going to do is use our knowledge about velocity, find where the object turns around, and it's going to turn around anytime its velocity equals 0. That's when it comes to rest, and then most likely will change direction. So what we're going to do is use the fact that velocity is negative, is moving in a negative direction, and positive velocity moves in a positive direction to help us figure out where is my total distance traveled negative so I can turn that around and make it positive. So that's where example 3 is going to come into play. We're studying the same particle that we did in example 2, where we saw its displacement was negative 10^3 meters, but we want to now find the total distance this guy traveled. So again, I'm given the same velocity function, the same time frame from 1 to 6, but now I'm being asked to find total distance. So what I want to do to find my total distance is first figure out where my velocity equaled 0 so I can start breaking up that interval from 1 to 6. So I'm going to take my velocity function, I'm going to set it equal to 0. I'm going to solve this quadratic. You can solve it by factoring, quadratic formula, graphing. I'm going to factor because this is a pretty basic function. And I'm going to solve for the t when I factor this. So I'm going to get t equals 4 and t equals negative 2. You're going to automatically throw out any negative time because in our problems, negative times don't make sense. So we're going to automatically toss out any negatives. And if we had multiple times that fit, we would also only make sure we're grabbing values between 1 and 6. And 4 is definitely between 1 and 6, so we're going to keep this guy. So now I know at 4 seconds my particle came to a rest. So I just want to see, well, between 1 and 4 to 6, what the heck was this particle doing? So I'm just going to do a quick number line. So I want to start at 1 and at 6, and now I know my particle did something at 4. Its velocity was 0. So what I'm going to do now is just find a test point in each interval and figure out was my velocity positive or negative. And what that's going to tell me is whether or not its displacement would be positive or negative, because it would be moving left to go a negative distance or right to go a positive distance. So if I pick a value between 1 and 4, like 2, and I plug it into my velocity function, I'm going to use the factored form right here because it's a lot easier to do the math if I do that. If I put 2 in here, I'm going to get 2 minus 4, which is a negative number. And here I'm going to get 2 plus 2, which is a positive number. And a negative times a positive would be a negative. I know my velocity between 1 and 4 would be negative, which means my particle is moving to the left, and so it would have a negative displacement. So to turn that around and make it positive, we're going to say it's the opposite of that value. Because a negative times a negative would be a positive. So if your velocity is moving negative on an interval, you're going to make the integral negative. And so now I'm going from 1 to 4 for my velocity function, which is that t squared minus 2t minus 8. Multiply that by my change in time, dt. And now I can figure out on this interval, how far did the object move? And by taking the opposite of that, I'm going to get a positive displacement. I'm going to repeat the process, and I'm going to go ahead and now look at 4 to 6 and see what's happening here. If I pick a value between 4 and 6, let's say 5. 5 minus 4 would be positive 1. 5 plus 2 would be positive 7. Positive times a positive stays positive. My particle is moving to the right on that interval, so I would get a positive displacement for this. So I'm going to add on, I'm going to keep this integral from 4 to 6 positive, using that same t squared minus 2t minus 8 for velocity dt. So now I'm still finding my total values from 1 to 4 and 4 to 6, which would give me my total distance traveled from 1 to 6. All right, so again, just like we do anytime we have a definite integral, I'm going to go ahead, I'm going to keep the negative sign out front of this first guy, and I'm going to go and anti-differentiate that function, which we did in example 2. It's still the same thing. It's at 1/3 t cubed minus t squared minus 8t. We're going to evaluate that from 1 to 4. And then I'm going to add on that same antiderivative, because it's the same function, evaluated from 4 to 6. Again, the rest of this now is calculator work. I'm going to go ahead into my calculator. I'm going to replace all my t's with 4 and get the value. Keep that negative there. So I'm going to put negative, and when I went through and replaced all of these t's with 4, and this should say t cubed, and that should say t cubed. There we go. When I go and replace all of those t's with 4, I ended up getting negative 80/3 for this first value. And I'm going to do minus. When I went ahead and replaced all those t's with 1 and worked it out, I got negative 26/3. We already did 6 from problem number 2, but to refresh your memory, when you replace all of these t's with 6, you ended up with negative 12. And we already put 4 in as our upper bound. That was that negative 80/3 there. If we've done this correctly now, what we should get here is a negative value that would multiply by a negative and turn this to a positive. And this should work out to be a positive so we can get our total distance traveled. So again, I went to my calculator, I took negative 80/3, subtracted negative 26/3 from it, then multiplied it by negative 1 and found out, oh wow, that was beautiful. It worked out to be just 18. Negative 12 minus negative 80/3 gave me some number I cannot read. Looks like 400. I can't read my handwriting there. Oh, well, that was 44/3. Really couldn't read my writing. So this all works out to be 44/3. And if we put those two pieces together, 18 plus 44/3 altogether gives me 98/3, or about 32.667 meters. So completely different from its displacement. Back in example 2, we said, oh, from start to finish, it moved negative 10/3 meters. And now all of a sudden we're saying it moved 32.667 meters. Big difference. So when we're looking at total distance traveled, we have to consider the negative velocity, and we have to consider that that's going to give me a negative net change, and I want to make that a positive change. So I'm going to go ahead and find my velocity by setting it equal to 0. I'm going to find my turning points. And then once I have my turning points, I'm going to break up my interval that I want to study. And where my velocity is negative, I'm going to make that a negative integral on that interval, and then a positive anytime my velocity is moving right. Let's finish up by looking at another example and connecting this back to the differential equations that we looked at the beginning of this unit. So back when we started this unit, we worked with our differential equations. Again, that's when we started talking about how the antiderivative of acceleration is velocity, the antiderivative of velocity is position. We were given some initial values, and we used those to find some functions. So we're going to connect those two things together. So in our final example here, in example 4, the acceleration of a function was given to us as 2t plus 3. And its velocity at time 0 is equal to negative 4. And we want to study the particle on the motion on the interval from 0 to 10. We want to find first its velocity function. And then once we have that, we can go ahead and find our total distance. So again, they want total distance. So first thing I'm going to do for part A, I'm going to find my velocity function by taking the antiderivative of my acceleration function. So if I anti-differentiate that guy, I'm going to get t squared plus 3t. And don't forget, when we're doing these general antiderivatives, we're going to put that plus c. When we're doing integrals with definite bounds, we don't need the plus c because it would just cancel out when we do f of b minus f of a. But when we're doing a general antiderivative, we need our plus c. Now we got to figure out, well, what the heck is c? I can't solve this problem if I don't know what c is. So now we're going to go ahead and take that consideration here that v of 0 is equal to -4. So I'm going to replace all of my t's with 0 and set that equal to -4. And I'm going to find out that c was -4. So now we know our velocity function was t squared plus 3t minus 4. That was my answer to part A. Hooray! Now that we know the velocity function, we could either use our net change theorem and find the displacement if they wanted me to. And again, I would just find the integral from 0 to 10 for my velocity function times dt. But here they want us in part B to find the total distance traveled. So to get my total distance traveled, I need to break up this interval from 0 to 10 so that anytime I get a negative displacement, I turn it around to a positive. So again, now that I have my velocity function, I'm going to go ahead, set it equal to 0 so I can find any turning points. I'm going to go ahead and factor this to solve the quadratic. Again, I'm going to automatically toss any negative times. They don't make sense. And then only use times that fit in my interval between 0 and 10. 1 does land. Hooray! So that means I'm definitely going to keep that one. And now the last thing I need to know is figure out, well, what direction is my particle moving on this interval? So I'm going to make my number line starting at 0, ending at 10, plopping in 1 somewhere on there. And I'm going to test my velocity function to see which chunk of this number line is my velocity moving negative, and which chunk of my number line is my velocity moving positive. So I pick something between 0 and 1. Let's pick 0.5. If I put 0.5 in here, this is going to stay positive. This guy is going to be negative because 0.5 is smaller than 1, so 0.5 minus 1 would be negative. A positive times a negative, we have ourselves a negative velocity from 0 to 1. So we're going to write our total distance is equal to the negative integral from 0 to 1. So we turn that negative around to a positive. And then we're going to use our velocity function times dt inside our integral there. So there's my distance moving from 0 to 1. And now let's find my distance from 1 to 10. Let's make sure he's moving to the right. I'll pick something in between like 5. 5 plus 4 is 9. 5 minus 1 is 4. 9 times 4 is positive. I'm moving to the right from 1 to 10. Therefore, I'm going to add on a positive integral from 1 to 10 for that same velocity function times dt. All right. The rest is just anti-differentiate and evaluate these integrals. So we're going to go ahead, anti-differentiate, we get 1/3 t cubed plus 3/2 t squared minus 4t, evaluated from 0 to 1. And don't forget that negative out front so that we can turn, this should work out to be negative when we do f of b minus f of a, so we can turn that negative to a positive. And then we're going to do that same, oh my goodness, why do I keep writing 2's instead of cubes? It's 1/3 t cubed plus 3/2 t squared minus 4t. And this time we're going from 1 to 10. All right, so once again, relying on my good old friend, the calculator, I'm going to go into this function, replace all those t's with 1. And when I did that, I got -13/6. Replace all those t's with 0. Well, that's nice and easy. I don't even need my calculator. That's 0. This is going to turn that negative around to a positive 13/6. On this guy, when I went in here and replaced all of those t's with 10, I got 1,330/3. And then I replace all of those with 1. We've already done that. That's that -13/6. When I went to my calculator and I took 1330 divided by 3 and added on that 13/6, it worked out beautifully to be 445.5. And so when I add them up, I found out this lovely particle moved a total of 444 and 2/3. I don't know what the meters per second or anything was, so we're just going to say units. We don't know what our distance was really. And that's our total distance. So we have to keep in mind net change is displacement, and that's going to tell me how far I moved from starting point to end point. And it's not going to consider negative motion. It's going to just kind of ignore any overlapping lengths that we had. So if your object goes left and then turns around and goes right, displacement ignores that overlapping. To get total distance traveled, we have to kind of bring in that negative velocity. And so we're going to find where my velocity is negative and break up my integral from 0 to 10 into 2 chunks. And if my velocity is negative, I'm going to create a negative integral for that chunk. And then where my velocity is positive, I'm going to create a positive integral for that chunk. I'm going to just apply the integral from the bounds of velocity times dt for each of those guys, and I differentiate and then do f of b minus f of a, and then add up our values, and that's our total distance. All right, so you have a couple practice problems to kind of summarize and review what we just discussed in this video, and then moving forward, we'll kind of just make sure we are doing good with this, and then start talking about what happens when we have integrals without these bounds.